calculates the hash of some input. We're going to see later in this talk how we can go about having hash functions. And then you have your main function where you define an input which is supposed to be kept private and an input which is public. And then you return true if the hash of your input matches the public hash. Pretty simple. That's pretty close to what you would actually write in Zokratis. And then this program is turned into a prover and a verifier, and the verifier can be run on the blockchain. So what it looks like for the whole pipeline of tools that we provide, so we have this high-level language, we have a compiler that takes that high-level language and turns it into a constraint system, and typically into a prover and a verifier. The prover runs on the client, basically, to compute witness, so basically executing the program and generate proofs. Whereas the verifier is actually a Solidity smart contract that can be directly deployed to the Ethereum blockchain, and which can verify the proofs generated by the prover. We also provide import statements so that we can import from different files and define more complex function and functionality. So that's great. However, for some of the use cases that I had described at the beginning, most of them require a hash function. And when you look at Zokratis language in general, it provides very basic functionalities such as adding, multiplying, if-else statements or for loops, but it doesn't have hashes, for example. So we implemented a hash. We went with SHA-256, and here's the results. Right, so our implementation has 250,000 constraints, which is about 10 times as many constraints as the Libsnark gadget. And we've identified some ways to improve it, but we really know that the Libsnark implementation is hand optimized, so there's very little chance that we're going to be able to have the same performance with a high-level language. Therefore, our strategy is going to be to include this performance which is provided by Libsnark and include that in Zokratis, being able to import those circuits from Libsnark. Pretty simple. So let's see how we could do that. When you look at those proof systems, so Zokratis and the Libsnark gadgets, which both enable developers to specify programs, they both rely on the same abstraction, which is called R1CS, or rank 1 constraint systems. And for those of you who don't know, it's basically a list of equations, like the one I described on this slide, which have variables which can be basically positive integers, which I'm going to call field elements. So it's basically any integer that's between 0 and a very, very big number. And you can basically do additions and multiplications, and then executing the program is basically finding an assignment to all those variables so that all the constraints are verified. So both Zokratis and Libsnark gadget rely on the same abstraction. Therefore, that was the best candidate we had at first to try and interoperate and import Libsnark gadgets into Zokratis. But when we looked at the implementation of SHA-256 in Libsnark, we found out that it had a very efficient way to do addition of binary numbers. So here, for example, an unsigned 8-bit number. If you have an array of bits and another array of bits, and you want to compute the sum of those two numbers and return the array of bits corresponding to the result. That sounds pretty simple. However, as I just described in the R1CS format, we only have access to additions and multiplication of integers. So that's actually not that simple to do. So the most naive way to do it is to use binary circuits. So here we have a binary adder for 2 bits. And it's basically each of those gates corresponds to one constraint, as I described earlier. And you basically add all of those binary adders so that for 32 bits you have a bunch of adders like this. And it's totally feasible. That's what we did. And in the end, you end up with about 1,000 constraints to add to 32-bit numbers. So that's already a lot of constraints. And in R1CS, the more constraints you have, and for those proof systems, the less efficient the system becomes. So let's see if we can do better than that. Here's an idea. So I represented it as a Zokrates function. Again, we take as inputs, so here for 2 bits, we take as inputs the bits of our inputs. So A1, A2, B1, B2. And then what we do is that at the first line, we calculate A as a field element, so going from bits to an integer. Second line, we do the same for B. At the third line, we add A and B to find C. This is very, very efficient. It's only one constraint because it's for field elements. And finally, we take C1 and C2 and assign that to the bit representation of C, right? And return that. So that sounds better. However, we have not really solved the problem. We just have moved the problem because like the first 3 lines are really easy, but the last line going from a field element to its bit representation using only additions and multiplications, that's very hard as well. And that's feasible, but that's also going to yield a lot of constraints. So here's maybe a better idea. So we start with the same, A1, A2, B1, B2. We turn the bits into the field elements. Then we add the 2. And then what we do is that we assign C1 and C2 to the bit representation of C off the band. So not directly in the circuit, but we just arbitrarily set C1 and C2 new variables to the bit representation of C. Does that make sense? But at this point, we could have put any values, right? And that's what was described in the previous talk about we could feed any junk data in our circuit. We could have put any values. So it's not enough to just set those values to the bits. We also need then a constraint which checks that this assignment actually verifies what we're trying to do, which is that C should be the sum of C1 times 2 plus C2 times 1. And here we have it all. So we have the sum in just about 4 constraints. And this is basically what sums up most of a lot of the performance that you get from using Libsnark gadgets versus like a high-level language, a naive high-level language, is that most of the computation is not done in the circuit itself. It's done off the circuit and then fed into the circuit and only verified into the circuit. And it takes advantage of the fact that for a lot of computation, it's way cheaper to check the computation rather than executing it. Also, the lesson that we learned from this is that R1CS, which is just the constraints themselves, so in this case, it would be line 1, 2, 3, and 5. This is not enough in order to kind of bring all the power of the Libsnark implementation into Zokratis. We also need to capture this hashtag line, which is not a constraint, which is just an assignment of the variables, and that needs to be part of the format. So great, we now have a format that we're using, so it's basically composed of 2 elements. The first element is the assertions, which is pretty much the constraint system. And then the second element are what we basically call helpers, which are those off-the-band operations which set some variables to some values, basically, in a very, very generic way. So how does that look like in practice? We use this kind of abstraction to integrate SHA-256 with Zokratis, and here's how it goes. We define a function, which is basically going to be a wrapper around the Libsnark SHA-256. It has a number of inputs. Actually, there's actually only 512 inputs. And then we have the constraint system, which is here with constraint, which is all the constraints from the Libsnark implementation. So that's those 27,000 constraints. And then before checking the constraints, we set every single variable in the constraint system to whatever Libsnark think it should be. So here at the V0 to V27,000, we basically call the witness generation function in Libsnark. So we ask Libsnark, hey, what are the values of all those 27,000 variables so that all those constraints are valid? So this runs inside Libsnark. And then in the constraints, we basically check that every single constraint is valid. And finally, we end up now with 27,500 variables. But actually, since we're computing a hash, we only need 256 results because that's the output. So we need to select out of those all those variables, we need to select everything we actually need as the output. And that's how we're doing it now. And we basically have a function, a working import of the Libsnark SHA-256 into Zokratis that can be used transparently. So where do we go from there? Right now, it's only for SHA-256, but it would be pretty easy to make that more generic and enable to connect to any Libsnark gadget. We also use this kind of construction internally for some of the languages features, which are also implemented as constraints and helpers. So sometimes we use Rust because our code base is in Rust, so we can write those helpers in Rust. Sometimes we use Zokratis itself because it can be also pretty useful to just have some Zokratis code that needs to be executed to find a witness. But maybe there's one final kind of caveat with this standard is that even though we have defined everything that's needed in order to port some gadget into another library, we still have two elements that are completely separated. So on the one hand, we have the constraint system, which gets imported. And then when trying to execute the program, we have to call this other library, so make a call to Libsnark and find a witness. It would be great for the space to have one self-contained format so that you can only import whatever program from a different library and then run it completely in your context. And for that, we're experimenting and looking at how, for example, WASM can help so that your format would be a constraint system as well as some WASM bytecode which captures the whole witness generation phase, which captures this whole helper, so that you don't need any low-level dependency. You don't need to call Libsnark at all. You can do everything in the same context. So some of the stuff we have on the roadmap, so there's more interoperability, so making those helpers as generic as possible and making it as easy as possible to export and import from different libraries. We're also working on a type system because currently we only have field elements as a type, and we want to be able to also talk about U32 numbers, for example. And all of the type system will be built on top of this notion of helpers and constraints. And finally, we currently have only an integration with the curve and proof systems that Ethereum uses, but we're also looking at how we can expand that so that we can compile to a prover and a verifier that could be run in different environments. So I think that's all for me. Feel free to try it out. We will also welcome contributions. And thank you very much for listening.